Okay, so we are looking at eigenvalues and eigenvectors. So let's just recap what we did yesterday. So yesterday we were saying that for a matrix A, Ax equal to lambda x, and here x is the eigenvector and lambda is the eigenvalue. Right. So this is what we have been looking at yesterday. And what did we do? Let's just recap what we did yesterday. So I'm going to give you I'm going to go back to our example yesterday. So we had this matrix A with 1, 2, minus 1, 4. And how did we say that we can find out its eigenvalues and eigenvectors? Can someone tell me? How can I find the eigenvalues of this matrix?
So we write another matrix B, which is A minus lambda I times.
Okay.
Yeah.
And then?
And then since this B comes from the equation Bx equal to 0, so the determinant of B should be 0. And then from there
Okay,
we
so we first find out. So first such that determinant of P, which is equal to determinant of A minus lambda I, is equal to 0, right? And 2. What do we do next? So this gives me the eigenvalues here, right? So these are my eigenvalues. How will I find out the eigenvectors? So I'm going to find out all. So I'm going to substitute this lambda. So these eigenvalues will be lambda 1, lambda 2 up to lambda n. And I'm going to substitute each of them here in A minus lambda. So I'm going to take I'm going to write A minus lambda 1 I. So lambda 1 is one value for which determinant of, so lambda 1 is such that A minus lambda 1 I is determinant of A minus lambda 1 I is 0. I'm going to write this, and then I'm going to find out that particular vector x, which gives me 0. Okay. So these x are eigenvectors. Okay. And then we said that in any matrix, so we are talking about square matrix, right? So in any square matrix, an n cross n square matrix, so here is a theorem which you can tell it's a theorem. In any n cross n square matrix has n eigenvalues. Some may be repeated. Okay, and so this is fine. This is all looks good. So algebraically, this is all fine. But what was so geometrically, what is the intuition behind the eigenvalues and vector? Who wants to recap? Tell me that. So geometrically, what is good about eigenvalues and vectors?
So eigenvectors after multiplication with a matrix A, they don't change the direction. They just grow in size or shrink in size.
Okay, so an eigenvector such that uh, if this is if V is an eigenvector for AV, let me, so AV will be something here which is on the same direction as V. So geometrically that's the intuition. V and AV are going to be in the same direction. Okay, so these are eigenvectors, and the eigenvalue is what is the extra magnitude the matrix is going to impart on the direction of V. Okay, this much is clear. Now, what else did we do? So after that, we looked at a few examples of eigenvalues, and so certain matrices for which we found out the eigenvalues and vectors. Kind of special matrices like identity matrix, diagonal matrix, etc. Now, let me go ahead. So we also said an important property of eigenvectors. So here is something we said. We also observed the following fact that there need not be an independent eigenvectors for a matrix A. Okay, so this is a crucial fact. There need not be an independent eigenvectors. Okay, so when a matrix A do not have any independent eigenvectors, these are called as degenerate matrices. These are matrices we are mostly not interested in. We are interested in non-degenerate matrices where there are, so our interest, matrices which have n independent independent eigenvectors. So this is what our interest is, and most matrices are going to satisfy this property. Most matrices has this property. Okay. So if you take if you write a Python program and to create a random matrix. So what do I mean by a random matrix? You take, just fix first a dimensionality, let's say 3 cross 3 matrix. Okay, and you're going to randomly choose some numbers here. Okay, so if you do that, highly likely you're going to end up with a matrix which has n independent eigenvectors. Okay, so most matrices are going to have this property, and these are the matrices we are going to be interested in. And as you will soon see that the kind of matrices we deal with will have this property. Okay. This one property we saw, and next is what about, we saw that. So this is let's see. I'm going to write a matrix. Right, my A is going to be okay. So let this be my matrix. What can you say is the sum of the eigenvalues?
So -5.
Yeah, so this is -5. And why is that? Because we know that the sum of the eigenvalues is the sum of the diagonal elements. Okay, so whatever is here, this is the sum. So this is equal to what is called as the trace of the matrix, or the sum of the diagonal elements. And we we also said that another property, that the product of the eigenvalues is equal to the determinant of it. Okay, right. We said this. We also observed. We looked at a special matrix. This is kind of a matrix, and 2, 3, -1, 0, 0, 0. So diagonal matrix, and what are its eigenvalues?
2, 3, -1.
Yeah, 2, 3, -1. Very crucial fact. Two eigenvalues are 2, 3, -1. And what are its eigenvectors?
So 1, 0, 0, 0, 1,
1, 0, 0,
0,
0,
1,
1, 0,
0.
and 0, 0, 1. What is special about these eigenvectors?
So this is the basis of the three-dimensional space.
They are basis, but there can be many bases for R3. Any independence, any three vectors which are independent are going to be a basis for R3.
Orthogonal. They are orthogonal.
They are orthogonal. Yeah. So I don't know who said these are the three bases. I mean, these are the three bases you usually see. I mean, like whenever you talk about R3, these are the kind of bases you usually see, and usually vectors are represented using these bases. That's what you're telling that. But I mean, but as you might have realized, any set of any three independent vectors are a basis for R3, right? So so that's not special, therefore, because I could have given another matrix and where there can be three other vectors which are independent, and they could have been also a basis for R3. But this is crucial that they are orthogonal. So this is an observation which right. What do I mean by orthogonal? We saw that earlier. What is orthogonal? Because their dot product gives me dot product is 0, right? That is the meaning. If you take the dot product of the first two vectors, it is 1 times 0, which is 0, plus 0 times 1, which is 0, plus 0 times 0 is 0. So that's the dot product of the first two vectors is 0, and the dot product of second and third is 0. The dot product of the first and third is 0, right? So they all have. So they are all orthogonal vectors. So if we talk about, so if this is my R3, X, Y, Z, and so these are perpendicular. So these are like this, right? These are my three vectors. Okay. So this is some factor which we will. I mean, I won't prove this fact, but this is something which it's good to observe, that all symmetric matrices we can find orthogonal eigenvectors, right? Okay. This is also clear. Now, next. Right, yeah. And this is going to help us in a lot of ways, which we will soon see. Anyway, going ahead, what else did we do? We looked at a few examples, and that's it. Yeah. Okay, so we'll proceed to what a further discussion on eigenvectors and eigenvalues. Let's see. Okay, so let me ask you another question. You should tell me yes or no and justify it. Okay. So I'm going to consider two matrices. Okay, two matrices. Okay, and their eigenvalues are so let's say the largest eigenvalue is lambda 1 here, and let's call here beta 1 here for B. These are the eigenvalues, so largest eigenvalue, let's say. Can we say that the eigenvalue of A plus B is this possible? This is correct? What is your intuition saying? Can this be true?
Sir, for 1 cross 1, it is true.
1 cross 1 matrix. 1 cross 1 matrix, you're saying?
Yes, sir.
Yeah, but
So it would depend on the eigenvector. If the eigenvector was the same for both, then it would be possible.
so let's see. Right, that's correct intuition. So let me explain that. Why? So what is happening? So let me assume that let x be the eigenvector for A. Okay, and x not eigenvector for B. Okay, so if that is the case, so if I take A plus B x, right, this is equal to ax plus bx, which is equal to lambda 1 x plus bx is not in the direction of x, right? This is not in direction of x. Why? It's not in direction of x because it's not an eigenvector for B. So therefore it's not in the direction of x. And therefore you can't get, if you do, you can't get lambda 1 plus beta 1 times x. This is not equal to this, right? That's what we wanted if you wanted x to be an eigenvector for A plus B. So therefore this is it's not always possible. But when is it possible? It's possible if x is also an eigenvector for B. Then so if both have the same eigenvector, if x is eigenvector for A and B, then A plus bx, what is it? This is equal to x plus bx, and this is same as lambda 1x plus beta 1x, which is equal to lambda 1 plus beta 1x, right? So if both have the same eigenvector, then you can add up that particular eigenvalue. That's a crucial factor, right? So it's so don't. So this is what is the takeaway from this? So the takeaway is that takeaway: don't add eigenvalues, right? I mean yeah. So this is, let me write it. Eigenvalues, values of A plus B is not sum of eigenvalues of A and B. Okay, so you should not like just simply add their eigenvalues and expect it to be. That's the catch. That's a mistake you can make. But what about this? Can you? So if A has eigenvalues 5 and 6. It's an example. Okay, I'm writing. A has eigenvalues 5 and 6. What about B, which is equal to A plus I? What is its eigenvalue?
Six and seven.
Yeah. Is this clear to anyone? Everyone? Why is this true? Because whatever. So we can argue this because if X. So. So let V1, V2 be, this is be eigen vectors of B of A, then we also know this fact V1 and V2 are eigenvectors of I. Something we saw earlier, because I times V1 is same as V1 with an eigenvalue lambda where lambda is 1. Similarly, I times V2 is V2. Its eigenvalue is also 1. So both V1 and V2 are eigenvectors of the identity matrix. This is true for any V1 and V2, right? Any vector is an eigenvector for the identity. Therefore, B V1 is same as A plus I times V1, which is equal to A V1 plus I V1, which is same as lambda V1 plus 1 V1 is equal to lambda plus 1 V1. So if A had eigenvalue 5, A plus I will have eigenvalue 6. And A had eigenvalue 6, so A plus I will have lambda value 7. So it's clear. Now it's also clear that the same ideas you can clearly extend to be equal to A plus 5i. If I write 5i, what will be its eigenvalue? Its eigenvalue will be lambda plus 5, where lambda is the eigenvalue for A. The eigenvalue for B will be lambda plus 5. Similarly, I could have written B is equal to A minus I. So lambda will be, the new eigenvalue will be lambda minus 1. Right. So B equal to A minus 7i will be lambda minus 7i. Right. So this is clear that you can now adding or subtracting with an identity matrix can basically you can get. I mean, you can add the you can increment and decrement the eigenvalues of the matrix. Okay, so this is about addition, and let's go to multiplication again. What about eigenvalues of AB? So A and B are matrices, and the with some eigenvalues. And what can we say about the eigenvalues of A and B? So eigenvalues of the matrix AB. The answer is, the answer is nothing much. So it's also not dependent on the eigenvalues of A and the eigenvalues of B. I mean there are special cases, but in general you can't tell about anything about the eigenvalues of the matrix AB. Okay, this much is clear. But what about eigen values and vectors of A square. So this is a special case of the previous the previous general case of AB. Here it's A square. What can I talk about the eigenvalues and vectors of A square?
So the same eigenvectors and the eigenvalues are squared.
Correct. So what is the answer? The answer is if lambda 1, lambda 2 up to lambda n are eigenvalues of A, then lambda 1 square, lambda 2 square up to lambda n square are eigenvalues of A square. Why is this true? And okay, so this is point number 1, and point number 2 is that they have the same eigenvector. Yeah, why is this true? Let's look at this. So let lambda 1 and v1 be eigenvalue and vector for A, right? So I'm going to so this is something I know. Lambda 1 is an eigenvalue for A, and v1 is its corresponding eigenvector. Okay, I'm going to do A square v1. What is this? This is same as A times A v1. But what is A v1? We can tell what is A v1 because A v1 is, we already know that v1 is an eigenvector for A with an eigenvalue lambda 1. So that's
Lambda 1 V1.
exactly. So this is lambda 1 v1. So this we can rewrite it as A times lambda 1 v1. And now since lambda 1 is a scalar, you can take it out. This becomes lambda 1 times A v1. Again, we know what is A v1. So this becomes lambda 1 times v1. This is what we were looking at, lambda 1 square v1. Okay, so we have A square v1 is equal to lambda 1 square v1, and therefore this is my eigenvalue and this is my eigenvector. So the eigenvector remains the same, which is same as v1, and the value is now squared. Good. What about A raised to 50? Should know the answer. The eigenvalues of A raised to 50?
Lambda raised to 50.
Yeah. So lambda 1 raised to 50, lambda 2 raised to 50, up to lambda n raised to 50 will be my eigenvalues of A raised to 50. And the eigenvectors will be v1, v2, which is the same as the eigenvectors of, so same as those of A. This is my eigenvectors. They are the same, and these are my eigenvalues, which are now raised to the power 50. These are all okay. So any doubts?
Sir, A square can have another lambda, which might not be the eigenvalue for A. So it can also happen.
Okay. Okay. So let's see. So A square. So A has lambda 1, lambda 2 up to lambda n eigenvalues, right? Which is n eigenvalues. And this is an n cross n matrix. This is an n eigenvalue. So what about A square? A square is also n cross n. It can also have only n eigenvalues, which we already told these are all its lambda 1 square, lambda 2 square up to lambda n square are already n eigenvalues. So, and an n cross n matrix can only have n eigenvalues. So now you can't have more. Is it clear?
Yes, sir.
Sir,
Yeah.
I have a doubt in this.
Huh.
Sir, suppose we have lambda 1 is equals to 2 and lambda 2 is equals to -2. So
Huh.
their square will be 2 or 4. Then
Lambda 1 is equal to 2.
and lambda 2 is equal to minus 2.
Huh.
Their square is 4. So how can we say that?
Huh.
Or-
Huh,
Hello?
so yeah. So now for a square. So for a, these are the eigenvalues. So for a square, eigenvalues are, there are two eigenvalues of 4. 2 square and minus 2 square.
Okay, sir.
Okay. Yeah, so this is correct that it can be that lambda 1 square is same as lambda 2 square. I'm not denying that. Okay. Yeah, that's good. This is good. So now what is next? Let's look at something else. These are yeah, something else is, so we are looking at the whatever the good matrices, right? So good matrices have what is a property? So my matrix A has n independent eigenvalues, vectors, independent eigenvectors. Okay, so I'm talking about such matrices. So A has n independent eigenvectors, and here is some things you can do for this. Now let me say I have a vector V. I have a vector V, some arbitrary vector. Okay, since I have a vector V, okay, before that, let me just write down so my independent n independent eigenvectors, I'm going to denote it by V1, V2, V3 up to Vn. These are my independent eigenvectors. Okay. Now I'm considering some arbitrary vector. Now V is used. Let me say let U be an arbitrary vector, something else. So it need not be V1, V2 to Vn. It's some other vector in Rn. Can I write U as a linear combination of V1 to Vn?
Yes, sir.
Yeah. What do I mean by that? What does it I mean by that statement? That U can be written as a linear combination of V1 to Vn?
Sir, it means that there exist constants C1 to Cn such that C1 V1 plus C2 V2 up to Cn Vn gives U.
Okay. So which means there exist C1, C2 up to Cn some constant such that C1 times V1 plus C2 times V2 plus up to Cn Vn is equal to U. Why am I able to do this? Why could I do that?
Sir,
Why
because
can't
all
you?
the
NR
VIs are
Yeah, one person, someone.
Sir, because all the VIs are independent, so they form the basis of n dimensional space.
So this is some, yeah, it comes from two crucial facts. Any other point? Devan, you were saying something?
So I think Bhavna was saying something.
You're saying
Sir,
the
I
same
was
thing.
saying the same. Yeah.
Okay, Bhavana, sorry. You were saying the same thing. Okay. What is it? Sorry, I mean, I missed. You are saying that V1 to Vn are the basis for, so this is the crucial fact. V1 to, so the crucial fact is that Rn can only have n independent vectors. Okay, that comes from the fact that any n independent set of vectors form a basis for Rn. Okay, so let me rewrite this. Any independent, any n independent set of vectors form a basis for Rn. Right. Any n independent set of vectors form a basis for Rn. So this basis difficult to read. Right. And these are independent vector, and we know that I'm telling you that v1 to vn are independent vectors, and therefore we have that v1 to vn form a basis. Right. This is right. And since they form a basis, you can, that's basically the idea behind basis, that you now using the basis you can represent any point in Rn using a linear combination of the vectors in basis. Right. So we have now we have come back to the fact that u can be written as a linear combination of v1 to vn. Right. Now I am asking you, assume that I already know the that's why, right? I already know the eigenvalues and eigenvectors of A. So now I want to find out AU. What is the answer? What is AU?
So C1 lambda 1 plus C2 lambda 2 plus. So linear combination of the lambdas.
Yeah, so let me write that. So this is A times C1 V1 plus C2 V2 plus up to Cn Vn, which is same as, I can now take A inside this bracket. That's the main idea. And this constant, I take it the other side. So it becomes A V1 plus C2 A V2 plus up to Cn A Vn. Right? And we know what is A V1 because these are all the eigenvectors of A. So this becomes C1 lambda 1 V1 plus C2 lambda 2 V2 plus up to Cn lambda and Vn. Right. This is good, but this does, yeah, this much is fine. This does not, as of now, this is good, but I mean, why do we go through all this pain? If I just wanted to compute AU, what is the use of all this? I mean, this is more painful method to compute AU, right? But what about I wanted A raised to 100U? Any idea what is the answer to that?
So then this method would be helpful.
Why?
So C1, it would just be C1 lambda 1 to the 100 into V1 plus C2 lambda 2 to the 100.
So this is C1. Yeah. Can you see this? Can you see why this is happening? Let me just do it for A square U. What is A square U? It's A times C1 lambda 1 V1 plus C2 lambda 2 V2 plus up to plus Cn lambda and Vn, right? And if I open that bracket, C1 and lambda 1, I can take it outside, and then I have A V1 plus C2 and lambda 2, I take it outside, and then A V2 plus up to Cn and lambda n and A Vn. Right, this gives me C1 lambda 1 square V1 plus C2 lambda 2 square V2 plus up to Cn lambda n square Vn, right? Okay. So this much is good. And so this, okay, now coming back here, why is this method now better? How much multiplication does, how many times do we have to multiply on the right side? How many multiplications are required here? So you have to multiply. Yeah, how do you do this multiplication? Let's maybe it's a slight sidetrack, but let's just look at so this is A is an n cross n matrix, and V is an it's a column vector of size 1 n. So how many multiplications are there in AV?
Sir, n square.
N square y. So v, okay, so let's just do this is my n cross n matrix, and this is my vector v. This is A and this is v. So, and I'm going to get something here, right? So this point, with how many numbers will this number multiply? This number is going to multiply with all these guys here, which is n. What about this number? This is going to get multiplied with all the numbers in the second column. So this is another n multiplication. Okay. And finally, so similarly, and finally, the last row element here is going to get multiplied with all the elements in the last column. So another n. So this gives me n square multiplications. Good. What about multiplying two matrices? Let's say a square, a. How many multiplications? N cube. Why?
Now you have n columns.
Now you have n. So we had already. So the first, if I multiply the first column with a, it gives me n square multiplication. Second column gives me n square multiplication. Similarly, n of them. So this gives me n cube multiplication. Okay. Now, what about, I am interested in doing, let's say, a cube b. How many multiplications are required? Let's do it for a square v first. What about a square v? How many multiplications are required?
n cube plus n square.
N cube plus n square. And how did you do? You first multiplied a. So you did this first.
Yes, sir.
And then you multiplied with v. Okay. Any other method?
A into AV.
A into AV. Yeah. So
AV.
if I do A into AV, how many multiplications?
That would be 2n square.
That will be 2n square. So which is better? Which is the better method? Obviously, which is the better method? We have to choose this, right? This is a better method. So when you have to do this, it's always better to first multiply with a vector and then do this. Keep on doing. Yeah. So open the bracket like this, right? Opening it like this. This is not a good method because that's going to give me order n cube multiplication, whereas this gives me order n square. So this is O n square. I hope you know this notation, right? This gives me O n square multiplication, and this gives me O n cube. So O n square is better, right? So now we know multiplication, and what about a cube v now? How many multiplications?
2n cube plus n square.
So 3n square. 2n cube plus n square. No, you're. You again went back to the. Went back to the.
Got it.
Yeah, you went back to the wrong method. No, you have to first multiply AV, get that vector, and then multiply again with AV, etc. So this is 3n square. So a raised to 100v, the number of multiplication is 100n square, right? These many multiplication. Okay, so anyway, we came there because we were looking at here. So this requires 100 multiplications. On the left, but on the right, how many? Sorry, 100 n square multiplication. But on the right, how many?
N square.
N square.
N square multiplication.
Yes, sir.
Sir, order of n multiplications.
It's 2n, yeah.
Like something like 102n.
How did you get N square? Yeah, I mean, we'll come back to this order N, but who said N square and what is the, can you tell me why you got N square?
So for every vector v1, it has n dimensions. So c1 lambda 1 to the power 100, which is a scalar. We have to multiply it by n components of this v1, and that's same for n lambda n. That's same for n numbers. That way.
So this much, how many multiplications here?
N, order of n.
Okay. Okay, so what is wrong? So something is wrong in my argument. Okay, so I wanted this to be order n. Maybe I am wrong. Okay, so it's good. I will come back and clarify it. Okay, this is not. It's not I wanted. Okay.
Sir, it's not order n, but it's much less computation if n is large.
Why?
Sir, because for v1 we have 101 plus n multiplications.
No, it is.
And
yeah.
Sir,
Yeah.
we'll calculate. Yes,
So
sir,
this is
101 plus n.
So this is 101 plus n. And n times
Similarly, we have n such rows. Yeah. So
Yeah,
we
so-
have n square plus 101 n, which is
so-
quite small.
Yeah, but yeah, but this is also order n square. Yeah, that's true. This is also, both are order n square. And but you're saying, yeah, this saves in some constants wise, this will be good, because I mean the other one was 100 n square. This is only n square plus 100 n, or 102 n or something like that. Yeah.
Sir, on the left, if you have in the power, if you have k, so left hand side it would be kn square, but on the right hand side it will be O of n square only.
If k is also a parameter, yeah, I agree. But if k is some constant like 100 or something, yeah, that is true. You are saying if okay. Yeah, so this is correct. Yeah, this is a good intuition. So it says that if once this 100, this becomes bigger and bigger, right? This method becomes better and better. That's our understanding, right? Right? If the power k gets bigger and bigger, the right hand side becomes better and better. Is that correct? If I say that, that's correct? because for a very large k, this is going to be k times n square, and on the other right side will only be n square plus kn. Right?
Yes, sir. Yes, sir.
So for a very large k, the right side is good, and for a small k, both seem to be kind of same. Yeah. Okay, so this is good. So now, yeah, we have understood this better now. Good. Now, since now let's move ahead. So this is one advantage of having this eigenvalue. So now we will see better some practical applications of eigenvalues soon. I mean not soon. I mean next lecture. But let me go to a new topic now. Okay, an important topic, and we'll finish with. We look at what are called as similar matrices, and then we finish with a diagonalization theorem. Okay, so diagonalization of matrices, and we finished that, and then next lecture we'll see some applications of eigenvalues and eigenvectors. Okay, we'll try to pick some natural examples and try to see how good they are. Yeah, why it will be useful in practice. Yeah. Now, what are called as similar matrices? Okay, so I'm going to talk about two matrices which are kind of similar, and the kind of idea. I mean, we are talking about eigenvalues and eigenvectors, right? And I'm going to say, I mean, the kind of thing which, I mean, when do I want two matrices to be similar? That what I would want is when the two matrices have the same eigenvalues. Okay, that's kind of the idea I'm having. But this is what I'm going to define it in a different way. I say that we say matrices A and B are similar if I can write A is equal to M, B, M inverse. Okay, so usually it's written the other way. So let me write it the other way. M inverse B, M. So there exists a M like this. There exists an M. If there exists an M like this, then I say that A and B are similar. Okay. Okay. You'll soon see why this is a good notion. And why now I'm going to argue the following. So if this is the case, yeah, so here is my claim. My claim is the following. A and B have same eigenvalues. Okay, this is my claim. And so let's try to prove that. So let lambda and v1 be lambda and v be eigenvalue and vector for A. So which means A v is equal to lambda v, or which means that M inverse B M v is equal to lambda v. Okay. What I'm going to do is that I'm going to multiply M on both sides. So on the right and on the left, it becomes M inverse B MV, and on the left, it becomes lambda MV. Okay. Now M inverse becomes an identity, so this is the same as B MV is equal to lambda MV. Now, can you see why is lambda an eigenvalue for B? Because look at this. So MV, take the vector MV, y is equal to MV, then B times y is equal to lambda y. Right? So lambda is also the So lambda is eigenvalue for B. Is this clear? Is that a, do you understand this?
Yes, sir.
Okay. So if we have this, so we say that A and B have the same eigenvalues if we can find a matrix M such that A is equal to M inverse Bn. You can multiply with M inverse on the left of B and the right of B, and then you get A. So they are similar matrix, and this is very useful. Actually, it's very useful in practice. Your MATLAB, yeah. So let's come back. Here's a problem. You are given a matrix A, and you are asked to find out its eigenvalues. How do you find that out? How have we found out till now? So given a matrix M, how do we? I mean, what is the method we know now to find out the eigenvalue? Yeah, I'm waiting for some answers.
Sir, if it's a general matrix, then we solve the n degree polynomial.
Yeah, so we solve the polynomial which we get by taking the determinant of A minus lambda I, right? And we solve an n degree polynomial. But I don't know if you know this, but can we solve any n degree polynomial? Do you know? Do you know of any method to solve an n degree polynomial?
No, sir. Not exactly.
No, sir.
Yeah, you don't know. You don't know why? Because it's not possible. So that is the that's called as. So there is so it's called as Galva theory. So Galva was I don't know which country. So he was a mathematician. So he showed the fact that if the degree is greater than 5, then you can't solve it. Okay, so if degree is greater than 5, there are polynomials which you can't solve like that. There is no method to find out its solution. Okay, so yeah, so that's a troublesome problem now, because the method we knew to find out the eigenvalue does not exist, because now we can't convert it in an n degree polynomial, and there is no algorithm to give me its solution, right? So yeah, so that's not a method which. So the method we have been trying to find out the determinant and trying to solve it. It works since we have been. As an example, we have been looking at two cross two matrices or 3 cross 2 matrices. I could show you that. Yeah, here is the eigenvalues, etc., etc. But that's not a useful thing to do when in practice. If you're looking at larger than 5 cross 5 matrices. Okay, so the main thing which we are going to, so the main idea which things like MATLAB and maybe other such applications do to solve the eigenvalues, to basically retrieve the eigenvalues of matrix. What they do is they try to come up with such matrices like this M. They try to come up with a matrix M such that when you multiply it, so let's say B is our matrix, and they're going to multiply it on both sides, like M inverse Bm, and they try to come up with a matrix like this such that when you multiply it, you're going to get a diagonal matrix. If I do that, if I get a diagonal matrix, what will happen?
The eigenvalues will be the diagonal entries.
Exactly. So that's the strategy which applications like MATLAB do. They try to come up with matrices M, and you multiply M inverse on the left and M on the right, such that once you do this multiplication, you are going to get a diagonal matrix. And we have already seen that once you have a diagonal matrix, everything is on the all your eigenvalues are on the diagonal. That's kind of the idea with which they work. We can maybe let's see we'll see whether we can look at some. We'll see later. Maybe see. I need to think whether we should go through these things. But if I feel or if you are interested, we can go through such things. So these are the kind of techniques which. So this theorem is the idea of notion of similar matrices. This is a very important tool to find out the eigenvalues. That's a crucial factor. Okay, now once you have this, so this is one. Okay, so what we have just now seen is an application of this, an application of similar matrices. So let me tell you another thing. Another consequence of similar matrices. AB and BA has same non-zero eigenvalues. So I'm saying that AB and BA have the same eigenvalues. Why can I say that? If I want to show that AB and BA have the same eigenvalues, what is it? What is the idea we know? We know that we have to show that they are similar matrices. If I can show that they are similar matrices, I am done. And if I have to show that they are similar matrices, I have to show that AB can be written as M inverse BAM. Yeah, can I do that? Can you find an M such that this is possible? Can you find an M such that AB is equal to M inverse BAM?
Yes, sir. Since B is similar to A, so
No. B is no nothing. I am not saying that B and A are similar. Okay, I'm just saying that AB and BA are similar. Any AB and BA, n cross n matrices, they are similar. Okay. So right now we will just talk about n cross n matrices, and that's why this came up. So let's. So I will just keep two as same eigenvalues. Okay. So A and B are n cross n matrices. So we are looking at square matrices. So A and B are n cross n matrices, any n cross n matrices, and I'm saying that AB and BA have same eigenvalues. Why? In fact, I am showing that AB and BA are similar matrices. If I have to show that AB and B are similar matrices, I have to come up with an M such that I can write AB is equal to M inverse BAM. Can you come up with an M which can do this?
Sir, if A is invertible, then we can have M is equal to A inverse.
Yeah. So is it A invertible or B invertible? A is okay. You're taking M to be A inverse. So yeah. So this has to be so we are talking about our n cross n invertible matrices. Okay. Yeah. N cross n invertible matrices. If we have that, take M to be you said A inverse. In that case, what do we get? AB is same as, what is M inverse? M inverse is A, PA times A inverse, which is same as AB, right? Okay, so we can pick M to be A inverse, and that's good. So that gives me AB and B have the same eigenvalues as long as they are both are invertible matrices, let's say. Okay. Now I could have even taken M to be B, right? Because I mean M inverse is B inverse, BA gives me A times B is AB. Okay, so right now we have found out that AB and B have the same eigenvalues, right? Okay, so finally, which is we have now picked out all kind of very good properties of eigenvalues, and then we are going to see the last property called as diagonalization. Okay. So here is the thing. Let me go back to our matrix we have been looking at. We had 1, 2, minus 1, 4. This was our matrix, and do you remember its eigenvectors and eigenvalue?
2, 3.
2, 3 was it? Right. So it's eigenvalues 2, 3, which gives me 5, and eigenvectors. So what is 1 minus 1? It gives me something. 2. Yeah, it gives me for the eigenvalue 2, 1 minus 1 is a vector. And for 3, do you remember? Or can you find that out now? Can you solve it and tell me what is the eigenvector corresponding to eigenvalue 3?
So it's 1 minus 2.
1 minus 2. Okay, so 1 minus 2 gives me 1 plus 3, and minus 8, which is minus 6. Okay, good. So this is these are the eigenvalues and eigenvector. Now I'm going to do the following. I'm going to write the same thing: 1, 2, minus 1, 4. This is my matrix A, right? This is my matrix A, and I'm going to multiply it with the eigenvectors. What do we get here?
Two, 3 minus 2 minus 6.
2, 3. Yeah. What are these columns? What are these columns?
Lambda 1 v1, lambda 2 v2.
Lambda 1, v1. So lambda 1, v1, and lambda 2, v2, right? Is that correct?
Yes, sir.
Right. I'm going to rewrite this right metric. So basically, I'm going to rewrite 2 minus 2, 3 minus 6 as okay. I'm going to write this as this multiplied with some other matrix here. What should be this some other matrix on the right? It has got to do something with the eigenvalues.
So the diagonals have eigenvalues, rest everything is 0.
Right, 2 3 0 0. This is correct. Can you just take a few seconds, maybe a minute, to just check whether this is correct? Convince yourself that everything I did here is correct. What does 2 0 do? 2 0 is going to pick up only the first vector, first column vector, right? The rest is 0, so that's gone. So this is gone. It's going to pick up the first column vector and multiply by 2, and that's exactly what we wanted here. 2 minus 2. The second vector is going to pick up the second column vector and multiply it by 3, and that's what we have here. Is that can you see this pattern? So I'm going to write this entire thing. I can write this entire thing like this: 1 2 minus 1 4, which is my matrix A, right? And I have my eigenvectors here: 1 minus 2. These are my eigenvectors. This is same as, again, my eigenvectors here, and these are my the diagonal entries are my eigenvalues. Do you all agree to this equation? You all agree?
Yes, sir.
Yes.
Yes, sir.
Okay. So how do I generalize? If I want to generalize this and write this as a theorem, what can I say? So I have a matrix A, right? And what can I say? So the matrix A times
V1, V2 up to Vn.
V1, V2 up to Vn. What is this equal to?
Same V1, V2 up to Vn into that matrix with lambdas as diagonals.
Right? You all agree to this? Why is this true? So what is the proof of this? We'll just quickly prove this. Why is this correct? I can write this V1 to Vn as AV1 to AVN, which is same as lambda 1 V1 to lambda n Vn, which is same as writing V1 to Vn here and lambda 1 to lambda n on the diagonal. Because, yeah, so maybe this I can clarify it. What is lambda 1 0 0 up to 0? If I multiply this column with this matrix, it is going to give me lambda 1 times V1. That's exactly what we wanted here. Right? That's exactly what we wanted here. Lambda 1 times this V1 gives me lambda 1 V1. Right? Okay. So this is then lambda 2. That's our theorem. Right? And so usually it's written in a slightly different manner because people, I mean, in a shorthand manner, where, let me write it. So usually lambda, so this capital lambda is your lambda 1 to lambda n, and S is supposed to be your V1 to Vn. Okay, so the eigenvectors here, eigenvector matrix is denoted by S, and sorry, sorry, I made a mistake. It's going to be denoted by X, and I mean, you could have used any other. I mean, we have written capital X because usually we write Ax equal to lambda x, right? So capital X for all the eigenvectors of X, and capital lambda for all the eigenvalues. So this is the eigenvalue matrix. and therefore the theorem is written as follows. Says that Ax is equal to x lambda. This is called as the diagonalization theorem. Right, so which says that any matrix A which has n independent eigenvectors can be diagonalized, or another way to write this is A is equal to x lambda x inverse. How did we get this? We multiplied x inverse on both the right side of on the left and right of the equation. This is the standard way of representing this diagonalization theorem. It says that the way to see it is that any matrix A can be V1 to Vn and with some diagonal elements here and followed by V1 to Vn inverse. So this is standard diagonalization theorem, and it can be done only if there are n independent eigenvectors, and this is something which we have been telling that most matrices are going to satisfy this condition. Okay. And now just before we leave, and what can I say about for symmetric matrices? So I am matrices, right? So what can I say about symmetric matrices? We said some things. Some things are special for symmetric matrices. What is so what? Yeah. So let me just recap what are the special things about symmetric. Real. So I'm talking about real symmetric matrices. Real eigenvalues to orthogonal eigenvectors. So n orthogonal eigenvectors. Yes. Now symmetric matrix, how can you write? Same equation you can write Q lambda Q inverse, right? Same using the diagonalization theorem. But what is Q inverse for an orthogonal matrix? Do you know?
Q transpose.
Yeah. So this is maybe some of you I don't know, but see, this is Q inverse is Q transpose for an orthogonal matrix. What is an orthogonal matrix? All column vectors are orthogonal to each other. Okay. So for an orthogonal matrix, it is yeah, I mean Q inverse is same as Q transpose, right? Good. So this okay. So for symmetric matrices, you get a much better diagonalization theorem, which says that Q gamma Q transpose. Okay, and this ends our yeah. I mean, we come to the end of the diagonalization. I mean, eigenvalues and diagonalization. And the next lecture, we will see some applications of this diagonalization, and in general about eigenvalues and eigenvectors and what, how, where can they be used, and how in practice where do we use it, and what. Yeah, that will be our aim next lecture. Okay, any doubts? So maybe I'll take just 5 more minutes just to, I have like one point I have written which I missed. So I have A is equal to x gamma x inverse. What about A square?
X gamma
Yeah.
square x inverse.
So let me just write x gamma x inverse, x gamma x inverse. This is, if I do open up this brackets, it becomes x inverse x becomes identity element, and this becomes x gamma square x inverse. Okay. What is gamma square? Gamma square is also a diagonal matrix. Is gamma square also a diagonal matrix? This is also a diagonal matrix. So diagonal matrix times a diagonal matrix is a diagonal matrix. Okay. And if we go ahead, what is a raised to 100? This is, you're going to get x. Right. So, I mean, we are coming back to the same idea which we have been telling. To compute a raised to 100, this is a much better method. That's the point I'm trying to make. So this takes off n cube. Right, sorry, I have to use. So this takes something like 100 n cube, because any matrix multiplication is n cube, and 100 times you have to do. So it's 100 n cube, maybe 99 n cube, but let's keep it 100 n cube. And on the right, it is this. We know how many multiplications are required. How many multiplications here?
Sir, 100 and
Yeah, so on the diagonal it's 100n, and then you have to do some with this and this. Yeah, so this comes out to be, so 100n gives me, yeah, so now it's basically multiplying 3. Yeah, so this is 100n plus. So once you have done 100n, you're going to multiply, let's just x, y, z. How much time does it take to multiply 3 matrices of n cross n? Yeah, I'm asking how much time to get this, to do this, the rest of the multiplication. So the middle part gives me 100n multiplications. What about the rest? It's just 3.
Sir, 2n cube.
Yeah, so it's 2n cube multiplication. So this comes out to be 100n plus 2n cube, and on the right, on the left, you have 100n cube. Again, what we observe is that the k, this k increases. So this is kn cube, and it's kn plus 2n cube. Okay. Again, as k increases, k becomes much bigger. This is a much better method to do multiplication. Okay, this comes to the end of this lecture here. Now let's meet next Monday. Any doubts? Any more doubts? Otherwise, we will stop. Okay, then I will stop the session. Thank you. Thanks, everyone.
Thank you very much, sir.
Thank you, sir.
Thank you.